Yes. Thanks, Mr. It is the joint research of Professor Czejdo from North Carolina State University, my student Szymon Katra, and me. First, I will show the motivation of the work. Then I will show basic formulas. Then I will enter into the language developed for specification and verification of web services, and I show you the debugging process, which is very important, and we go to conclusion. What is the goal? The goal is to develop high-level programming language for web services and their verification. The language should reflect distribution, very important feature, asynchronic in distributed environment, locality of actions in machines, and should support automatic verification, because engineers do not need to learn temporal logics and environments with those mathematics, and interpretation of results, which is very important in the process. The basic model, integrated model of distributed systems, is built on observation that in distributed environment there is, among others, some server, and some message comes to the server, causing the server to execute some action which changes the state of the server, the new state, and issues the new message on output. Those two messages, input and output one, are in the context of some distributed computation called agent. And the agent comes with its message to other server. So the model is in Cartesian product of messages and states, messages of agents and states of servers, times messages and states, input ones and output ones. So we can imagine that there are states and messages. If the message matches the state, some action is executed, and it produces new message and new state. So the servers is very important because states are not atoms. The server has a state and offers some services and executes actions. So the state is a per state, the server is vague. On the other hand, agents represent distributed computations. So agent has a current message, which leads this agent, which calls server services. And using those messages, the agent travels between servers. So the message is a triple agent, server, and service. We can say that the agents calls the service on the server. We can imagine that from one server to another, the server is a simple semaphore, but distributed semaphore. The agent calls wait operation, which means that it comes to the right-hand server with wait operation. It's the service of the server. Then the action is executed on the server, changing the state up to state down. In opposite direction, the OK message is directed to the calling server. This model is used to verify distributed system. Our environment automatically finds deadlocks, total and partial. inevitable termination of processes, total and partial, and possible termination, total and partial. And the model, which is very important, supports strong fairness, because weak fairness or no fairness, which is present in many verification environments, is not suitable for distributed environment. This is how our tool works. This is the model, this is the verification, and this is sequence diagram, which shows how the system falls into a dead. This is the code used. It's simply a set of actions with no order. So there are message and state, new message and new state, and some syntactic glue to not to repeat the servers, to have types of server and establish many instances of them. And initialization are initial states of servers and initial messages of agents. This is used in our teaching. Over 400 students use this environment to verify their solutions, but the programming in such a declarative environment is not easy, is boring and error-prone. And we use, of course, not only for teaching, for other verification purposes as well. So we started to build more sophisticated language for web services. We assume that there are processing servers which organize some algorithms, distributed algorithms, and they call resources servers that are reactive. They offer some services. We structured the state of servers with many variables. So the state is a Cartesian product of values of variables in a server. And in processing server, we allow to start many agents, everyone with its own variable acting as a program counter. So its current position in the program. Of course, they are added to the set of variables of this server. Such a way, we achieve an environment in which we program in high-level language the web services. Then we translate to low-level IMDS code, which is also very important. It has the same semantics. It's different grouping of actions, but they are still the same set of actions. So after verification, when we find a deadlock or verified termination, we have a counterexample or a witness in the case of termination, and we can interpret this on source code. This is example of the high-level Ribu for web services code. We have reactive servers, which have instructions like garbage commands also. Processing server, in which have processes that call the reactive servers. These are actions that are more powerful. So single action in Ribu for web services is translated into many actions in the low-level code, but the semantics is the same. And here we have multiple processes with possibility of termination or acting in endless loops. This is a debugger in which we can show the counterexample on the source code, high-level code of the system. This is the source code of the Ribu for web services. These are the values of variables in servers, and these are messages of current messages of agents. And we can run the counterexample or witness or execute in step-by-step mode. So this is an example how the debugger comes to the instructions and shows what's going on with the system. This programming language is a youngest child in the family of domain-specific languages established on a common principle. There are other languages are restricted business process model and notation. The other is for relay interlocking systems. The third one is for railway control systems. We are building the fourth one for smart contracts, the fifth one, because there are already for web services. All of them have the common principle. The syntax in each language is different, but all the languages have the same semantics. Thanks to this, we can interpret the result of verification on the source code, which is familiar to the users, to the designers in given what?
The source code or source representation.
Or but in given area of application.
Okay.
Oh. Okay, so it's everything.
Thank you very much.
The basic model you can learn from my book, Integrated Model of Distributed Systems. I will show you in the spring essays.
Well, it's time for questions, please.
Yeah.
This is about the developer detection. What method we use?
It's CTL logic, computation tree logic, with our own evaluation algorithm, which is strongly fair, which is very important. But perhaps we use other verifiers like UPAL, but UPAL has no fairness. SPIN has only weak fairness. SNV has weak fairness, and only if you specify fairness instructions, special fairness instructions. Our is strongly fair, so it's suitable for distributed systems.
More questions? Maybe one. How your specifications can become platform independent in terms of technology? It means to specify the things in a way that can be generated for many different platforms.
We specify the system as a set of actions. Those actions are differently expressed in terms of relay circuitry, differently in terms of trains over the line, but they are specified as tuples. State, message, new state, new message.
It's always like that.
So, it's always like that. So the semantics of every of our domain-specific languages is exactly the same. The syntax differs dramatically.
Thank you. Another question, please. There are questions? If no, thank you very much.
Thank you.